Good morning to you. Supposed to say and you, man. Anyway. Alright, it's like Mary Poppins or something like that, so. Anyway, that's even before my time. Alright, corollary, derivative of the reciprocal of a function. So, now, I hate using this term because I can't say it. So, I hate it because I can't say it. Anyway, so if a function g is differentiable, that means I can take the derivative of it, then 1 over g would be the same as equal to negative the derivative of g over g squared. So the derivative of 1 over g is going to be the same as negative g prime over g squared. So, it means the same thing. Derivative of 1 over g is equal to negative g prime over g squared. So, all that is just, it's 1 over g, so it's doing the quotient rule of that function right there. With the derivative of 1, what is the derivative of 1? What's the derivative of 1?
1.
Just 1. Is 0. Because it's a constant, right? It's a constant, so it drops off. So, I know, it's kind of early in the morning, so we're trying this. Alright, so here is another way of actually saying it. Right here, there is my g prime, and this is g squared. So, it means the same thing. This is just another example of it. Alright, so, using this. So, this is, what is my g in this case? Just x, right? Because if I rewrite it, that's going to be d dx of 1 over x, right? Say yes.
Yes.
Okay, so if I go back to that first slide we started off with, so it said g prime over g squared, right? So it's a, right there. Can't forget that thing. So, just using that information, so I'm going to end up with a negative right here, right? Now, what is g prime? What's going to be the derivative of x? Just the x part. Just the x. So I'm saying g is x. So it's going to be 1 over g squared is x squared. Now, you could do all this using the quotient rule, or you could do it kind of like we did it. How did we do it earlier? We moved everything to the numerator, didn't we? So if I were to do the derivative of this as is, so x to the negative 1, so what did I say to do? It goes up front, right, and subtract 1. So that's going to give me, negative, right, to negative 2, right? So rewrite that with a positive exponent, so it's a negative 1 over x squared. We just move it back down to the denominator. So doing the corollary and all that other stuff, it's not necessary if you know how to move it. Just move it to the numerator. Because we like to move it. We like to? Thank you. All right. Okay. All right, did I confuse everyone already? Anyone lost? Okay, so I want you to, right now, do these right now. Now. On your notes, right now. You're doing these two right now. Write me out. Let's see if you paid attention. warm in here when I got here. It was gross. Okay, what? What? What?
I did move this back to the denominator now. Right now, it's a negative exponent, and so it changes to a positive exponent when I move it across the denominator, or divisor, right there.
Yeah, but I mean, like, you know how, like, the thing says here, you have to put the, G prime over
G prime.
G squared.
What's G in this case? G is just x, right? G is just x, so the derivative, so G prime, so the derivative of x is 1, okay? It's negative over the square.
Alright, you could do this either method. So let's try this now. So if I did this correctly, I know it's going to become a negative. And if G is U squared, the derivative of G, so G prime, would be 2U over G squared. So U squared squared is going to be U to the 4th, right? That's supposed to be a U. Looks kind of like a 4 though. Okay, so U to the 4th, right? And then I could cancel out one of my U's. Negative 2 to the U3. If you would have moved this to the numerator and did the calculus right there, do the derivative, you would have got the same answer. Either way, same thing. All right, this next one. So if I do this next one the same way, so the derivative, so I know it's going to be a negative. It's going to be 5s to the 4th. 5 times 4 is 20. S to the 4th over s to the 5 squared, right? So 5 squared is going to give me 10. Yeah, because it's going to look like this. It's s to the 5th squared. Yeah? So right there, I'm going to combine, and we're going to get, let me see, that's going to be negative 20 s to the 4th over s to the 10, which gives me negative 20, no s's, no s's, over s to the 6th. So either way you did it, you'll get the same thing. Some of these are actually just easier if you move the variable to the numerator. Find second, third, and fourth derivatives of this. So notation. This is the function. So the first derivative would be y prime. So take the derivative of 2x to the third. That's going to give me 6x squared. Now the second derivative, so y double prime, would be 12x, right? And y triple prime, 12. And y, this changes it right here, y 4. 0.
So the first one's velocity. The second
Yes, in a function. So that if this was s, so s of t is position. All right, we'll get into this later, but this is good to know now because you're already going to have problems about this. So it's kind of like expecting you to actually know what physics is. So S of t is position. and then s prime of t, which is also referred to as v of t, is my velocity. Spell velocity.
V-L-O.
V-L-O?
V-E-L.
V-L.
O-C-I-T-Y.
Velocity?
Yeah.
Okay. Velocity. Sounds like a French name. Velocity. Alright, anyway, alright, so S double prime of t, or referred to as V prime of t, is the same as saying A just A of t acceleration. Spell it.
A-C-C-E-L-E-R-A-C-I-O-N.
There you go. Acceleration. And this last one.
Double prime of V.
Yeah, it would be, but I'm not going to put all those. This is one that you will not use. You'll have to get to the derivative there, but you won't have to use it. So, this one is special. So, if I ever call someone the third derivative, just know it's an insult.
Wait, isn't it the fourth derivative? Oh, oh yeah.
It's the jerk. Alright.
Kill something else.
Next one, find the second and third derivatives of this. Now, first, it is a product rule, right?
Yes.
Okay, so I could treat it as such, or I could distribute. Either way, it's still going to end up being product no matter what. So, remember the other day when I said, you know, sometimes you're going to have to multiply as is, or you're just going to, you know, distribute. This is going to be one, no matter what, you're still going to have to use a product rule. So if I do the math, it's going to be y equals e to the x, right? E to the x plus e to the x squared. So either way, no matter what, you're not going to get away from actually having to do multiple of this. But this piece right here is actually going to be super easy. That's why I actually did this first. Alright, so let's go ahead and do the derivative. So this is a product rule. If you remember product rule, that is going to be f prime g plus g prime f. So let's see, it's going to be y prime. What's the derivative of e to the x? E to the x, alright. So I have e to the x, and then plus, that's super important, plus sign right there. Now, sometimes you guys are going to end up with a minus sign. You have to minus and then parentheses, because you have to distribute the negative. That's going to be one of the bigger problems that we're going to have here, is keeping track of positive and negatives when you have something like this, and it's going to end up having a plus sign in between. Because right here, actually, let me just do the math and I'll show you why. All right, so remember, f. So in this case, my f is e to the x, right? Yes? So f prime is e to the x. G is going to be x squared. G prime is 2x. Does everyone agree? Okay, remember the other day when I said whenever you're doing this, okay, until you guys get the hang of this and don't need it no more, go through and actually write it out. We're going to get into some harder problems later on, which are kind of tricky. I still do this. I still do this all the way through, because sometimes you're going to have, you know, to do this 3 or 4 times. So, anyway, so f prime, so it's going to be e to the x. G is going to be x squared plus g prime, which is 2x, and then f, which is e to the x. Now, the reason why I said it's important about the paying attention to this sign right here, because all this was actually one thing that came from here. It came from right up here. And since it showed up from right there, if there was a minus sign there, I would have to distribute the negative into my whole thing. That's super important to understand. So that will change a lot. So there's my first derivative. The second derivative, okay, I'm going to keep doing the same thing. So second derivative, like I said, you're going to end up having to do this a couple times. Now, I already know what this is right here, right? I could take the derivative of this because isn't it the same as this? Wow, it just got quiet.
Yeah.
Who'd I lose? All right, so this is all this, isn't it?
Yeah, that's the derivative.
It's the derivative of this right here. And I'm going to take the derivative of each thing individually. So it's a little bit less work for me. I know that y double prime is going to be the derivative of e to the x is e to the x. Okay? That one's all right. But now this piece right here, right? This next piece. It's already a product rule, but isn't this the same product rule that I had up here? Yeah, it's the same thing. So can I just write down this answer again? Say yes.
Yes.
Okay, so I'm going to have plus e to the x, x squared plus 2x e to the x, right? And now I'm doing the derivative of the last part, which is just this right here. Does that make sense now?
Yeah.
Did I catch you up? Okay, good. So now, I did the derivative of this, which just so happened to be all that under black right there, right? So it was there, and now I still have to do the derivative of 2x e to the x. So I'm going to go off to the side. So in this case, my f, nope, can't do that one. My f is 2x, my f prime is 2, g is e to the x, g prime is e to the x. Alright, so now, right here, I'm sorry, right there, so it's going to give me f prime, which is 2, and then g, e to the x, plus g prime, e to the x, and then f, right, which is 2x. So there's my second derivative. Okay, some of these actually get long. Now, if I were to rewrite this, we can go through it. Does everything have an e to the x? Say yes.
Yes.
It does. Everything does have an e to the x. So if it all has an e to the x, we can take that out. So I want to try and combine as much as I can right now. So let's take a look. Y double prime is equal to e to the x. So if I take that out, that's going to be 1, right? Say yes.
Yeah.
So it's going to be 1. And I have an x squared here, right?
Yeah.
Do I have another x squared? No, no other x squared. So it's going to be plus x squared. All right, what about my 2x? I have a 2x here, and I have a 2x here. So how many x's do I have?
4x.
Okay, so plus 4x. And what else do I have? I have a 2, right? So I could take that out. So 2, so that's plus 2. Oh, hey, can't I just put it over here
Yes.
with that 1? So I could change that to a 3. Plus 3. So it is going to get long. Some of these actually get pretty complicated. Simplify as much as you can. Combine like terms as much as you can. All right. So we have to do the third. So do I have another page here? Not yet. I will. So what was that? Y double prime was e to the x quantity.
X squared plus 4x plus 2.
All right, so it's a product rule again. So in this case, my f is what? E to the x, f prime. G, what's my g? X squared plus 4x plus 3. G prime. So derivative is 2x plus 4. All right, let's put everything where it goes now. So it's going to be f prime. So it's f prime. So it's going to be e to the x times g, which is all of that, x squared plus 4x plus 3 plus g prime, or I'm just going to put my e to the x first, g prime, which is 2x plus 4, right there. Now, do they both have an e to the x? Yeah, this is going to make life a whole lot easier to combine it like this. So if I take out an e to the x, I'm left with x squared plus 4x plus 3 plus 2x plus 4. So I can go through and combine like terms. E to the x quantity x squared plus 6x plus 7. Definition acceleration. For an object in rectilinear motion, its distance s from the origin at time given by a function s of t, the first derivative ds dt. So that means the derivative of s in terms of t, so my variable's t, is the velocity v of t of the object at time t. Acceleration a of t is an object at time t. It is defined at the rate of change of velocity with respect to time. So it is the derivative of the velocity. So, okay, so one way to actually say this, the second derivative of position is acceleration. Okay, so this is another way to actually write the second derivative. Now, I like nerdy shows, like super nerdy shows, like Big Bang Theory, but not like the drama of Big Bang Theory, like the nerd stuff. One of the ones that I find hilarious, there's the episode where he's Sheldon, his barber died or something, and so he went like a whole month without getting a haircut. So and he said, you know, his hair, he could actually feel his hair growing at, you know, 9.27 meters, 9.2 centimeters per second. So per second it means seconds squared. That means that, now, when we talk about velocity, that's time over distance. So it is, or I'm sorry, distance over time. So it's going to be the, like, feet per second. So I'm traveling that many feet per second. So that's going to be a constant velocity. But the velocity of, the derivative velocity gives me acceleration. So it is going to be accelerating. So it's the slope of my rate of change. So if my slope is increasing, so it could be my slope is increasing like this, but it's increasing at a certain rate. And so it's going to be increasing at a rate of per second per second. So velocity is, hey, how fast were you going as you're driving through that, school zone this morning? No pun on anything happened here last Friday. Okay, so now, 70 miles an hour in a school zone. Okay, miles per hour. 70 miles per hour in a school zone, right? That means if you think about it and picture it, someone's actually at that speedometer and they're looking 70 miles per hour. But then that cop that did the little radar gun to figure out how fast they're going, they only figured it out at 1 second, at a certain time. That was instantaneous velocity. So at the time that person drove through the cop's radar at 70 miles per hour, that was only right there. But they were speeding up. So they're speeding up. And so they were speeding up at a faster rate. Or they were slowing down because they saw the cop. But at that second, we said 70 miles per hour. So if you imagine it, they're doing 70 miles per hour for the whole time. If you're thinking about it. But they're actually not. You had a stoplight over there. So you accelerate from the stoplight, over through the school zone. And so it's actually per second per second. So it's the slope of the rate of change. So it could be increasing or it could be decreasing, depending on what you're doing. So what that means is, I really wish I could actually, go out there and like blow stuff up, because that's always helps. I don't know, but yes. Anyway, we are going to get into some more problems on this. So it's the per second is super important whenever talking about acceleration, because it's second squared on that one. All right, well, yes, we will get into it later. So, analyze vertical motion. A ball is propelled vertically upward with the ground at initial velocity. Okay? Initial velocity. So, at this many meters per second, and height s in meters of the ball above the ground. So, height s, there's my s of t. So, here's my function that's going to describe my height at that time, where t is the number of seconds that elapse from the moment the ball is released. Okay, what is the velocity of the ball at time t? So I would take this information right here, right? Okay, I would take this information and do what? Find the derivative. So it's going to be s prime of t is going to be, what's it, 9.8? Negative 9.8 t, right? And, plus 29.4, right? So there is my velocity at whatever time t. So I'm hoping I'm not, boring people to death.
That makes sense.
All right, so there's that one. Okay, when is the ball going to reach its maximum height? Now, if you think about it, maximum height, it's going up, isn't it?
Yeah.
Newton's law says must come down, right? So at some point, it's going to stop going up, and it's going to start going down. So at that point right there, what would I call that? The maximum, right? So when I'm looking for that, I know that it's no longer, so it's no longer going to be going up, it's going to be going down. So the slope or the rate of change is now going to go from a positive to a negative, isn't it?
Yes.
So in between those means I need to find what? Not the corner, yes. So it's going up, 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 right? And then down, 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 down. What's the slope at the top? 0. Thank you. That's what I needed. So whenever we're finding the maximum, the slope is equal to 0. That's like a super important thing. All right, so set it equals 0 equals negative 9.8 t plus 29.4. So negative 29.4 is equal to negative 9.8 t. So t is about not 3, like 2 point something. It's not 3. It's close. Like 2.9. It is 3? Exactly?
Yeah.
Wow, okay. My math is not working very good today. Is 3, exactly. Dang, okay, so let me change that to equals. Alright, there we go. So, we say the maximum of this ball is going to be at 3. This is when. So this is a t value, right? Say yes.
Yes.
Okay, so it says what is the maximum height? Now, if I'm looking for the maximum height, where does that, what information am I looking for? Y, right? In this case, but it's the S of t, right? That's the position, right? That's what I'm looking for. So I'm looking for that. So I plug what number? 3, because that's when it's going to be the maximum, into the position function. So plug 3 into my position function. So S of 3 is, yeah, do it. Yeah, you do it.
I'll go it.
It's going to be a, yeah. Yes, S. S, not the derivative. So if I plug this into the derivative, I should get 0, right? Because I just set it equal to 0 and solve for that. Negative what?
Negative 14.1.
I
I got 44.1.
44.1? Yeah.
Oh, are we supposed to subtract? Oh, we're adding. Oops.
Yeah. So. S. Where's S? 29.4 times 3 also. That's what you missed. Alright, so what was it? 44 point? So 44.1. What are my units here? Meters, thank you. Position, it's just meters. Just like this is going to be in what? Seconds, right? What is the acceleration of the ball at time t? So I would take the derivative of the derivative. Okay, so that's S double prime of t is going to be negative 9.8. And what would I say that this one's going to be? Is that a constant? Yes.
44.1 meters?
Yeah.
We're doing that by multiplying 3 times negative 4.9, right? So what happened to the 29.4 t?
Was that 20?
0.4 times 3.
Because you have to plug in 3 here and 3 there.
Right.
So we're plugging it into the original, this thing right here.
Yeah. So my question is, how's it 44.1?
Yeah, 500 and then
That's only the first, that's when you only get that if you do 4.9 times 9 times 3 squared.
Is there an error?
You get what I'm saying?
I do.
When you do SST, SS3, you only plug it in for the negative 4.9 times 3 squared. But there's a whole nother part, there's a 29.4.
Yeah. Let me see your math.
Oh, I didn't really say it.
Yeah. Yeah, right there. Okay. All right. Thank you. All right. So, where are we at now? Okay. So for this right here, we got negative 9.8. Did anyone take physics before?
Yeah.
Take physics.
Okay. What is so miraculous about that number right there?
Oh, that's gravity.
Gravity! That means that it is pulling down at negative 9.8, right? Negative 9.8. So it's pulling down at negative 9.8. So, negative 9.8 what?
Meters per second squared.
Meters per second squared. Per second. So, as you're falling, you're accelerating to the rate of this negative 9.8 meters per second.
Is that how fast things fall? Like,
Yeah, that's gravity. That's gravitational pull. So you could actually keep falling, but you end up at a certain point getting to terminal velocity or your like wind resistance and a couple other things that go along with that. But yeah, so the gravity, so the Earth pulls at that all the time. So just so you know, y'all have the weight of the world on your shoulders all the time. That was deep, right there.
You only got the weight of the gravity of the Earth.
But it's of the world.
It's not of the world. It's the weight of
Okay,
the
listen, they're not. This is not mythology. It's not Greek mythology here. You are not Atlas. Okay, you are not going to shoulder the whole world. Okay, if you were to do a headstand, then yes, stand on your head, and you can say that you have the weight of the world on your shoulders.
Oh.
Okay, there we go. Yes.
wait, so that's gravity, but gravity for what is being thrown?
Okay, this is the acceleration, right? It's acceleration, so that means that my ball, as it goes up, right? As it goes up, there's no longer any velocity at all, except for what's pulling it down. Right? So I throw it, and no matter what, because I have a force greater than what my downward acceleration is, my downward acceleration will eventually stop my forward momentum and start pulling it towards Earth, right? That's what this is doing. So now I throw it hard, it goes up, okay? All right, wait, hold on, you ready? Wow, I guess no one got that one. All right, so, and it gets to a point, then all of a sudden it stops accelerating, and it starts going down because it keeps pulling it down at that. So if I had a positive acceleration, what would that mean?
Floating on.
It would keep going, right? So if I fill that tennis ball full of helium, like concentrated helium, I've seen it, people do it, and you throw it, this thing could keep going and going, okay? But eventually acceleration Earth still pulls it down. Anyway, all right, so anyway, I like the problems. These are all good, talking about all this stuff. Tomorrow I got something special for you people, so don't forget, like, share, and subscribe.